if they had asked me what I would call the concept we now call basis, I would probably have come up with something like a pillar set or a pillaring set or a columnade or something like this, something reflecting the image you have in front of you. So I guess you're glad that I was not asked to name that concept, because of course the word basis is a lot shorter and easier to use. But why would I have come up with that idea? Well, because the idea of a basis is basically to identify what it is that sustains a whole vector space, what holds it up in a way. On the other hand, of course, this is just an analogy, so it just goes as far as analogies normally go. So let's have a look at what this concept really is and why it is so important for vector space. By the way, this is a fairly simple concept, one that you're not going to have difficulties in actually understanding, but probably the difficulties will come up in applying it, putting it to work, as well as in figuring out all the consequences that stem from it. So let's have a look at what it is that we're talking about. What we're really focusing on is the fact that we've seen recently that spans and subspaces are really the same thing. Remember, the span of every set of vectors forms a subspace, and every subspace is actually spanned by something. Okay? And of course that can be applied also to entire vector spaces, because when you think about it, even the whole vector space can be thought of as a subspace. It is a set of vectors in the space, it forms a vector space, so it is a subspace. It's a bit of a stretched idea of a subspace, but it can be considered as such. In fact, most mathematicians would consider it as such. So what is the difference between spans and subspaces then, if they're the same thing? Why do we separate the two concepts? Well, because in subspaces what we're focusing on is the axioms. Do we have a vector space structure? On the other hand, in the idea of spans, we're focusing on which ones are the fundamental vectors, the ones that are able to generate all other vectors in the space. So we're focusing on the idea of linear combination, but not from the axioms point of view, but from the constructive point of view. Okay? So what we're going to be looking at is a key question that still relates these two concepts. Okay, so we have a subspace and we have a span, and the idea is, can we find the smallest set or a smallest set of vectors that is needed to span a subspace? Let me show you a picture just to visualize this idea a little bit more. Let's say that this big cloud is our subspace or our vector space. So we know that this is going to be spanned by some set of vectors. And let's say that these are the vectors that we have identified as spanning this whole subspace. So let's say that we know that if we take all these vectors and we consider all their linear combinations, we come up with everything in the subspace. Now the question is, do we need all of those, or can we throw some away? Or perhaps more focused and more accurate way, what we want to ask is, which one do we need to keep so that we're still going to end up generating the whole subspace? Okay, so this is the key question that we're going to look at. Now I'm going to present to you both the concepts of basis and dimension. I'm going to first define what dimension means. We've seen the concept of dimension before, but only for Euclidean vectors and for the case of infinitely many spanning set and so on and so on, but we're going to formalize it a little bit more for general vector spaces, and then I'm going to introduce the idea of a basis. It can be done the other way around. I could actually first define a basis and then define dimension and with respect to it. So I'll leave it up to you to figure out how to do the other way around. So let's have a look at this idea of dimension, but from a more formal, more algebraic point of view. We have looked at it in the context of Euclidean vectors. We simply counted the number of components. We have looked at it in the context of saying, well, there are some vector spaces that cannot be spanned by any finite set of vectors, therefore it's infinite dimensional. But let's make it a little bit more formal. Okay, so we're going to say that a vector space that can be spanned by a set of n vectors but cannot be spanned by a set of n minus 1 vectors, we said that that vector space has dimension n. So, put in different words, again, I don't like definitions because they seem like very immobile and written in stone. I prefer the idea of a description. So the dimension of a vector space is the size of the smallest set that can be used to span the whole vector space. right? So let's look at some examples, some very basic examples. So if we look at a line through the origin, we have seen before that it has dimension 1. Why is that? Well, if we look at a line through the origin, it would look like this. And if I pick any vector which is along that line, then all the other vectors on that line, remember, of course, I'm identifying points and vectors in this case, but all the vectors on that line are going to be multiple and therefore linear combinations of that single vector. So all I need is one vector to generate the whole line, and therefore we're going to say that this line has dimension 1. This very much fits with our old idea of dimension, but it makes it a little bit more formal, again, more algebraic. The old idea was more geometric. This is more algebraic. Similarly, if I look at a plane through the origin, we have said it has dimension 2. Well, it has a width and a height, right, or a width and a length. And again, that is a geometric way of thinking about it. But the way to think about it is the fact that in order to identify a plane, if you remember from the vector equation, I need two vectors, right? And remember at that point when we looked at the fact that the vector equation of a plane needed two vectors, I sort of gave it as a given that it can be done. But in this case, we're looking at that as a basic property. So we're going to say is that, well, in order to get a plane, I need two vectors. Can I do it with just one? No, I can't, because if I only use one of those two vectors, say, all I get is the vectors which are parallel to it and nothing else in the rest of the plane. Therefore, the plane can be generated by two vectors, not by one. Therefore, it has dimension 2.